electrical, come on. I can't read. Alrighty, welcome to chapter 25. Chapters 25 and 26 are both about random variables. Chapter 25 is about discrete random variables. Chapter 26 will be about continuous random variables. Both of these chapters are going to incorporate concepts from chapter 23, so things like the mean and the standard deviation, as well as chapter 24, so looking at probability, except now we're not going to look at the probability of individual events, but we'll actually be looking at what's called distributions of events, and more about that later. This video is just going to explain what are discrete random variables, what are, in general, discrete probability distributions, although we're really interested in two particular distributions, which we see down there in sections F and G. And then we'll finish up with expectations. All right, so for starters, what do we even mean by a random variable? I don't know. When I first saw this word, I was thinking, like, aren't all variables like random or whatever? Don't overthink it, kids. A random variable is just the possible outcomes that could occur for a given experiment. Okay, and to denote the random variable, we tend to use this capital letter X. Okay, and the capital letter X, that is the random variable. That random variable can take on different possible values, which will be indicated by lowercase x's, and in this case, subscripts as well. So in this general sense, there are n possible outcomes. Each of them are x1, x2, x3, and so on up to x sub n, comprising the random variable capital letter X. The discrete random variable, capital letter X. Okay, and it means, to say that it's discrete means that they're things that we can count. It means that there are certainly going to be gaps in between the values. So the examples we see here, a discrete random variable could be the number of, and the rest of this phrase doesn't even matter. The point is it's the number of, it's something that we're counting. So houses in your suburb which have a power safety switch. I don't even know what that means. So whatever. Here, this one's a little more understandable. The number of new bicycles sold each year by a bicycle store. Clearly those are integer values in both, actually in all three of these examples, they're integer values. The number of defective light bulbs, blah, blah, blah. Discrete random variable does not need to be integers necessarily, although I'll say most of the time it will be. Just to compare to chapter 26, continuous random variable, this is more about things that we measure. So heights of people, they're in between any two heights, there's another possible height. Right? So that data is continuous. There are no gaps. Volume of water. Yeah, volume is going to vary continuously. So anyway, this chapter is all about discrete random variables. Let's get into it a little more. What is a probability distribution? Really, it's just a visual representation, either in a table or a graph, perhaps, that shows all the different outcomes and each of the probabilities of those associated outcomes. It's got some weird notation. So reading this line here, so remember we have our random variable capital X, and the probability that capital X takes on a particular value, little x, can be denoted this way. Now that sounds funny to say out loud, the probability that x equals x, but remember that the two x's just represent different things. So, for example, if we're tossing two coins, and we're counting the number of heads that we get, obviously we could either have 0 or 1 or 2. The probability that x equals 0 is 1/4. The probability x equals 1 is 1/2. The probability x equals 2 is 1/4 again. So down below here we have a graph of the probability distribution of number of heads for flipping two coins. Notice here, as well as in every probability distribution, when we add up all of the probabilities of all the outcomes, we should get 1 as our total. But we already knew that, right? Okay, so here's another really easy one with a slightly different looking probability distribution. So first, take a moment to read this over. There's a lot of weird words and phrases up here, but the problem is very, very simple. Okay, so a random variable x is going to be the number of accurate weighing scales in the supermarket. And there are a total of 3 weighing scales. So what values could x take on? Well, either none of them will be accurate, or 1 will be accurate, or 2 will be accurate, or 3 will be accurate. So x could either be 0, 1, 2, or 3. Now, since it says list the possible outcomes, let's be really specific here. Here they are. Okay, so we've got n if it's not accurate, y if it is accurate. And then in the right-hand column, x is representing just how many of them were accurate. So like I said, 0, 1, 2, or 3. Great. And this is basically a probability distribution. If I could just add one column, I would say, what's the probability that x equals x? And first would be if x is 0, if little x is 0, then that probability would be, well, 1 out of 8. The next would be if x is 1, and that would be 3 out of 8. If x is 2, that would also be 3 out of 8. And then if x is 3, 1 out of 8. Again, the probabilities add up to 1. Great. This example and the previous one were both symmetrical. That's not always the case. That's just a coincidence. Letter B, describe using x the events of there being one accurate scale, or at least one accurate scale. What does that mean? It just means, like, if there's one accurate scale, it means x equals 1. If there's at least 1, it means x equals 1, 2, or 3. That's all that's going on here. All right, we are into section B now. Section B opens up by recapping a little bit from section A. So up here in our blue box, the probability of each individual outcome must be somewhere in between 0 and 1. The sum of those individual probabilities must equal 1. And this describes the probability distribution of capital letter X. This is just a sequence of probabilities listed out in order from little x equals 1 to little x equals little I equals 1 to little I equals n, since using that notation up there. Anyway, we can talk about the mode of these distributions, and it's just going to be the most frequently occurring value of the variable. So in, let's actually go back to, in this case, the mode was 1. Here, we would say it was actually bimodal. There were 2 modes, 1 and 2. We can have the median is going to be wherever the 50th percentile is, but it might also just be the place where the cumulative sum reaches 0.5. So looking back at the previous ones, in this case, the median is going to also be 1 because my probability got to 50% somewhere in that column. We had only 25% here. By the time we got through all that, we're at 75%. So clearly 1 was the median. And in this case, it would be 1 would be the median, I would say, because, well, it depends on how you want to interpret this. As we covered back in chapter 23, there's actually multiple different ways to interpret quite a few things in probability. So you might say that 1 is the median in this case because when we add up these 4, we've got 50%. You might also say that 1.5 is the median since that's halfway between those, and 50% is, you know, kind of exactly in between the two. No right answer in this case, but don't worry. If it's ever crucial for you to know, it'll be obvious. You won't have to decide between the two. Okay. And down at the bottom, we can give a probability distribution in table form, in graph form, or even in function form. So in the previous 2 examples we saw here, I kind of tried to make this into a bit of a table. That's, I think, the most common that we'll end up seeing. You could have a graph. I think it would be the least common. Function form is also pretty rare, but we're definitely going to look at examples of that so we can see how that would work. Okay, it's important to notice that when we use function form, that the domain is only the possible values of the variable. Okay, I'm not going to make a big deal out of it, but you notice here that there is a name for this. We can call it the probability mass function. In certain ways, it can be useful to think of probability as mass of a physical object. So that's where this name comes from. Later on, we might see something called the probability density function as well. So there are physical interpretations of a lot of these things, but you don't need to worry about knowing that vocabulary. I think just calling it a probability distribution function will be fine for us. So here's one with a table, okay? So these are probabilities of Jason scoring home runs in any game during his baseball career. Okay, so we got a whole lot of values here. So hey, what's the probability, or sorry, what's the value of P of 2? That's the probability that he hits 2 home runs in a game. That's very easy. We look at the table and it's 0.1088. Finding the value of A. Well, since all of these probabilities need to add up to 1 in this row, that means we're just going to do 1 minus all of those, and that's going to give us a value. I don't know what that value is. Grab a calculator and figure it out. That's what the value of A is. What does that value, what does that number mean? That is the probability that Jason hits no home runs in a game in his baseball career. Finding the value of P of 1 plus P of 2 and so on to P of 5. Explain what this means. Okay, so that's, you know, these numbers added up again. I'm not going to do it. What does it mean? That's the probability that Jason hits at least 1 home run in each game, or in a game during his baseball career. Okay, draw a probability distribution spike graph. So a spike graph is just one where we have, let's do 0. I'm putting 0 out here because I don't want to see it on the y-axis. Nothing wrong with that. 2, 3, 5. Okay, so a spike graph literally just has a spike come up at each of these values. So 1 would go up to wherever, 0.3, 2 would go up lower, 3 would go up even lower. Usually we put dots at the very end just to kind of see it. 4 is even lower, 5 is actually down there, and 0, since I didn't calculate what it was, I don't know, but it's probably bigger than 1, given that home runs are rare. Eyeballing the rest of those numbers is going to be pretty big. Oh, and I should label these, right? This is x, and this is the probability that x equals x. Okay, and finally the mode and the median. Okay, so the mode is going to be 0 because that's the highest spike, and the median is also going to be 0. Okay, we do need to kind of figure out what A is, so just quick calculation here. We've got like 0.3 and 0.4. Sorry, 0.1 makes 0.4, and then a little bit extra. So A is going to be 0.5 something. It's a little bit bigger than 0.5, and that makes A the median because we've hit 0.5 already. Okay, let's do some more. So now we've got functions. Okay, so we need to find out what K is for each of these distributions. This is very easy. Here we go. I'm going to make a table with x and the probability that x equals x. Okay, my x values are only 1, 2, or 3. When x is 1, my probability is going to be 3k. When x is 2, my probability is going to be 4k, and when it's 3, it's going to be 5k. What do I know about 3k, 4k, and 5k? They have to equal 1, so this makes 12k equal to 1, so k must be equal to 1/12. That's the idea there. That's what you would do anytime that you have a probability distribution function. You should use that function to generate a table. Okay, same thing over there with letter B. I'm not going to do it though. Next up, this is awesome. Look at this function. Oh my gosh, we have binomial expansion now. This is great. Okay, so let's read through this. We've got electrical components produced and being packed into boxes of 10. Timeout. Notice that we've got tens happening here. Okay. We know that 4%, 4% of the components are faulty. So in other words, 96% of them are not faulty. Our random variable will denote the number of faulty items in the box. Okay, so now this whole binomial expansion function kind of makes sense, right? We've got 10 components in each box, and little x is going to be the number of faulty ones in that particular box. We can find the probability of big X equaling little x. Clearly, it's going to be 0.04 to the power of x, right? Clearly, then it's going to be 0.96 to the 10 minus x, since if they're not faulty, the amount of not faulty ones has to be 10 minus the number of faulty ones. And then because we might have different orderings of these things, we've got to do 10 choose x. Oof. What a problem. Anyway, the probability that a randomly selected box will not contain a faulty component means that x is going to be 0. So that's just going to be 10 choose 0, which is going to be 1, times 0.04 to the power of 0, which is going to be 1, times 0.96 to the power of 10, which is going to be surprisingly small when we grab a calculator. That's going to come out to be about 0.665. So that sucks. I don't want to buy things from this company. And then the probability that it'll have at least one. Well, I don't want to take this formula and put in 1 and 2 and 3 all the way up to 10. No, no, no. We're just going to do 1 minus the probability that there's none, which is 0.665. So that's going to come out to be 0.335. Okay, here's another one. We're just seeing different looking problems. So now we've got dice. We're rolling a pair of dice, and n is our new random variable. It denotes the difference between the numbers on the top faces. So let's make this the positive difference, okay? And let's display the possible results in a table. So these are two 6-sided dice. So what are the possible differences we might see? Well, they might be the same, in which case the difference would be 0. And at most, we could have a 1 and a 6, in which case the difference would be 5. So we're going to go all the way from 0 to 5. Now we're going to work out what those probabilities are. Well, in order to do this, it might actually help to have a table of what the rolls might be. So there it is. I didn't really feel like writing that all out. So we've got the 1 through 6 on the top and on the left, and in the middle we've got the differences between the rolls. So what's the probability of getting a 0? That's going to be 6 out of 36. What's the probability of getting a 1? Looks like that's going to be 10 out of 36. 2 seems like it's going to be 8 out of 36. 3, we've got 6 out of 36. 4, we've got 4 out of 36. And finally for 5, we've got 2 out of 36. Okay. Quick check. Do those add up to 36 out of 36? I sure hope so. Now we can go on to letter, we've just done A and B, so now we can do letter C. What's the probability that n is equal to 3? Oh, okay, we've just worked that out. Just look at the table. That's going to be 6 out of 36. What's the probability that n is greater than or equal to 3, given that n is greater than or equal to 1? So this is now conditional probability. Yes! So that's going to be the probability that n is greater than or equal to 3 and n is greater than or equal to 1 divided by the probability that n is greater than or equal to 1. The probability that n is greater than or equal to 3 and is greater than or equal to 1 is really just the probability that n is greater than or equal to 3, right? The denominator stays the same. And then we just calculate this from the table. The probability that n is greater than or equal to 3 is going to be, adding those 3 up, that's going to be 12 out of 36. The probability that's greater than or equal to 1 is going to be just subtracting that out. That's going to be 30 out of 36. Simplifying that, we get 12 out of 30. Okay, this problem is so exciting because it introduces the vocabulary of power series, which is actually, that's included in the option calculus topic. So depending on, kind of when in the core you're watching this video, you may not have seen that before. That's okay. You don't need to know this for the HL core, but if we're given this definition, we can still use it. So yeah, I'm not going to justify this. If you haven't seen power series, and this might look strange, but it turns out e to the x, that function can be rewritten as an infinite series with polynomials. So we can remove e from it altogether. Crazy stuff. Anyhow, we're going to now use that to evaluate this series down below, which I'm going to rewrite. I'm just going to take out the e to the negative 0.2 because that's not being affected by this this sigma, because the sigma has n varying. So what do we got? We got 0.2 to the n over n factorial. Okay. Now let's use their advice, right? They say use the definition above. Your first inclination might be to take this and rewrite it as an infinite series. That's e to the negative 0.2, so that should be equal to 1 plus negative 0.2 plus negative 0.2 squared divided by 2 factorial plus negative 0.2 cubed divided by 3 factorial and so on. That's actually not the quick way to go here. No, instead, we're going to actually work it backwards, because look at this. If we were to set n equal to 0.2, then those two expressions would match. So if n is equal to if x is equal to 0.2, then this series is really just equal to e to the 0.2. So this leaves us with e to the negative 0.2 times e to the 0.2, which is all equal to e to the 0, which is equal to 1. So the answer for letter A here, this entire thing ends up being equal to 1. Pretty wild. Okay, suppose x is now it's a random variable, a discrete random variable, representing the number of cars passing a shop in this 3-minute span. The probability distribution is given by this here. So it looks kind of similar to what we had above. I think letter A is not related to letter B so much in a direct fashion, but the expressions are kind of similar. Well, they're very similar, and as I said, it just has a really nice connection to some topics from the options. So it's a good problem. And Roman numeral 1, explain why this is a valid probability distribution. So that question means, or an answer to that is always going to be really just, hey, all these probabilities, they add up to 1. Okay, now had we not done letter A, it would not be obvious that these probabilities are going to add up to 1, right? We're substituting this infinite set of values into that expression, and that's not an easy thing to evaluate even for any particular individual value of x. I mean, if I put 0 in there, then I get 0.2 to the 0, so that's 1 multiplied by e to the negative 0.2 divided by 0 factorial, which is 1. So I still have e to the negative 0.2. I mean, I'm supposed to add that to a whole bunch of stuff and get 1 out? No, it's going to be really tough to do. But we worked out in part 1 that the sum has to be equal to 1. And, look really closely. This is the exact same expression as we have there. We've just changed the n's into x's. So why is it a valid probability distribution? because all the probabilities add up to 1. Letter B, Roman numeral 2 has us evaluating, well, what's the probability that x equals 0? Well, x equals 0, that's the one I just said before, right? When I make little x equal to 0, we're going to get just e to the negative 0.2. Whatever, you grab a calculator, whatever that is. For x equals 1, we're going to get 0.2 times e to the negative 0.2. That's it. Yeah, and so on. Roman numeral 3, find the probability that at least 3 cars will pass the shop. Well, we can't do 3 and 4 and 5 and so on and so on and so on. But what we could do is we could do 1 minus all 3 of those, right? Because everything else is going to be 3 or above. Anyway, that was a pretty nasty looking question, but it's not that bad. As long as you have a calculator at your side, you can do all the stuff in part B. And yeah, just like I said, a really nice connection to connecting calculus and statistics, which are often viewed as being on kind of opposite ends of the mathematical spectrum. So I think it's nice when two seemingly unrelated topics come together like this. Makes me happy. Anyway, let's finish this up. We're now in section C, which is called expectations. Okay, so up top, if we have n trials and the probability of a particular event is p, then the number of times we expect that to occur is going to be n times p. So we take the probability multiplied by the number of trials. Think about that for a minute. Should make sense. For a random variable, a discrete random variable, the expected value of it, the expected outcome, is given by these formulas here. It's really just the mean of the distribution. So that's the sum of each of the values multiplied by their individual probabilities. And that could also be rewritten using probability distribution notation there, P of x equals x and whatnot. Down below, we might talk about games being fair. Okay, games will be fair if the expected value of a game is 0. So, like, to put that into context, you know, if you play a game at a carnival or something, and you pay $1 to play. For the game to be fair, you should be gaining back, on average, $1. So that your expected value when you walk away from that game should be exactly 0. You've neither won nor lost money. That would be a fair game. Okay, so here is one such gambling game. Okay, you roll a dice, and if you roll a 6, you win 10. If you roll a 4 or 5, you win 4. If you roll a 1, 2, or 3, you win $1. Sounds great, except don't forget to play the game. You need to pay $4. Okay, so what are your chances of playing one game and winning 10? Well, that's clearly 1 out of 6. 4, it's going to be 2 out of 6. 1, 3 out of 6. Super easy. Okay, so they're using this phrase now. Your expected return from throwing a 6 is 1/6 multiplied by 10. Okay, what that means is you have 1/6 probability of throwing a 6, and if you throw a 6, you get $10. So what's your expected return from throwing a 4 or a 5? Well, the probability of getting a 4 or a 5 is 2/6. If we do that, we get 4 back. So that's 8/6 of a dollar. A little more than $1 back. Your expected return on a 1, 2, or 3, so that's going to be, let's just call it 1/2, multiplied by 1. So your expected return there is $0.50. And on a 1, 2, 3, 4, 5, or 6, well, we're going to take the expected return from a 6, which is 10/6, We'll add that to our expected return from the 1 to the 4 or 5, and then we'll add that to the expected return for a 1, 2, or 3, which instead of 1/2, we'll write that as 3/6. So our expected return here is going to be 21/6. In other words, if we play this game many times, on average, the amount we'll get back is $21/6. Okay, that's our overall expected result of just our winnings. Now, if we have to remember that we are paying $4 to play, and $4, that's going to be negative 24/6 of a dollar. So our overall expected result at the end of one game is going to be our winnings of 21/6, but we then need to subtract the amount we paid. So that's going to give us negative 3/6 or negative 1/2. So this is not a fair game, and why should it be? You know, when you play games like this, you should be expecting to lose money in the long run. And what's our expected result at the end of 100 games? Well, it's just going to be that multiplied by 100. Okay, whether a problem prompts you to or not, I think a really good thing to do is to write down what the probability distribution is. So in this case, let's let x equal the number of heads. So probability that x equals x, we could have, we're playing with a pair of coins, so we're either going to have 1 or 2 or 3. The probability of no heads happening, we know this from earlier, that's going to be 1/2. The probability, 1/4. The probability of one head showing up is going to be 1/2, and the probability of, I wrote 3, I don't know what I'm doing, of 2 heads showing up is also going to be 1/4. And then I'm just going to put the payout here. Okay, if we get if we have no heads, then we're going to lose £5. If we have one head, then we're going to win £3, and if we have 2, then we're going to win £10. Okay, how much should you expect to win playing this game once? It's really easy. We're just going to multiply the probabilities by the payout and add them together. So playing this game exactly once is going to be negative 5/4 plus 3/2 plus 10/4. So that's going to be 11/4. Okay. Now the organizer of the game, obviously, they want to make money in the long run, and currently the organizer is actually losing money because the person playing is gaining. We could make this a fair game by charging 11/4 of a pound to play the game. But the organizer doesn't want it to be a fair game. They want to make an average of £1 per game. So we need to charge £1 more than 11/4 of a pound. So we should be charging here 15/4 of a pound, or 3 3/4 of a pound. I think that's enough for these sections. We'll jump in the next video looking at variance and standard deviation, and then some properties of expected value and variance. We'll have some more formulas in the data booklet to take note of, and then we'll get into the real good stuff at the end of the chapter. But this is pretty foundational here. Every once in a while you'll see questions that are just about generic oddball probability distributions, as we saw here. The main points to take out of it are just, the probabilities need to add up to 1. How can you figure out the median and the mode? And how can you calculate the expected value of it? But nothing in this video was really terribly challenging. So I hope you agree, and I'll see you next time.